counting. What's that? Counting? Yeah. I mean, we learned, you guys missed yesterday, we calculated the probability of winning Pick 4 Ohio Lottery, right? And one of the things about doing this is we realized that it really is important to be able to count quickly. So here's a favorite problem of mine. Let's count the number of possible license plates in Ohio. Now, I have to say something. Do not include good old vanity plates, right? They call them? That's not the real name. What's the real name? Personalized license plates? You guys know what I'm talking about? What's that? Vanity? I mean, that's what we always call them. I don't know if that's a good way to sell them. But the reason they said don't include those is because then you could write anything, right? But how do license plates work? I mean, what's the basic structure? You have letters and numbers, right? How many? 7 what? Okay, there's 7 digits. Does it matter which? I think, don't the first 3 have to be letters and then the next 4 are numbers, right? I know because my license plates, it's hard for me to remember which one's which, but I know it's GAK, G-A-K, right? So you have, and I think that might tell you where you bought it. But anyways, you have, so let me put down, G-A-K, and then you have 4 numbers. Let me give all my personal information, huh? No, I mean, anyways. So you put your letters down, right? But they don't have to be G-A-K. But we were talking about yesterday this idea of a tree diagram, right? So remember we were doing heads or tails? And so we talked about, hey, heads or tails, right? And then we said, well, this one could be head, because we were talking about what's the probability of flipping heads twice in a row or something like that. I forget what it was. But this idea carries along. This idea is what you might call the fundamental counting principle. And what I guess maybe a brief way to state it is that making choices is equivalent to multiplying by the number of possibilities. Matter of fact, it's kind of funny because you know what I'm doing? As I pick which digits go here, I'm making choices. How many choices are there for the last digit of a license plate? Yeah, there's 10 different choices, right? You have 0 through 9. Okay. How many choices are there for this digit? Yeah. 10, right? Actually, and if you multiply all those together, wasn't that the pick 4 problem yesterday? So already, there are more license plates possible in Ohio than the number of pick 4 numbers you could get, right? There's more than 10,000. Because just with GAK, if you multiply this together, it's 10,000, right? There's 10,000 different arrangements of digits you could have after the GAK. GAK 0000, GAK 0001. Yeah, Jared? I agree. Each time we make a choice here, we're choosing one of 26 letters, right? So if you want to answer the question, how many different license plates are possible? That's the answer. You multiply all that together. And see, most of you may be too young. Well, not all of you, but many of you will not remember. See, when I was growing up, I could still remember my parents' license plates. Why? I don't know, weird kid. LJK 593 and LJK 594. Those were the two. But notice what's the difference. Used to be LJK 593, right? There were only 3 digits. So why do we have more now? More people started driving. More people owned cars. You go around some neighborhoods in the greater Cleveland area, you'll see houses with one-car garages, right? It was rare for a family to have more than one car. And nowadays, that's a lot more common, right? So, you know, these are, I think, interesting aspects here. Let's compute here. So how do you do this? Let's get the actual answers. So 26. Now, do you know what to hit next to do this quickly? You want to hit the caret key. Have I shown you guys that? Right here above the divided by sign. That makes an exponent happen. See that? And now if I hit the right arrow, that gets me out of the exponent. And I'm going to say times, and then it would be 10. Well, let me do 10 caret 3, because this is how many license plates there used to be when I was growing up. How many? What's that say? Yeah. How big? 17 million, right? 17 million. 17.5 million, you could say, right? That's how many cars we used to be able to accommodate in Ohio. Now, do we know how many people live in Ohio? I don't know. I know in the greater Cleveland area you might have about 2.5 million. Greater Cleveland area. That's the largest city. But all over Ohio? See, I think what happened was we started pushing the limits of number of cars. And they realized we're going to run out of license plates. That's when the law was changed. So now, right, how many license plates are possible? If you multiply that by 10, it's not 17 million now. How many are possible? 175 million. Guys, we're safe for a while. By the way, I can remember I took a family trip. You guys, I think I even have the photo up on my computer sometimes. I don't know if it's there now. But my kids and I went to Wyoming, to Grand Teton National Park. We took a family trip out there. And I remember seeing Wyoming license plates that had 2 letters and 2 numbers. That's it. Least populated state in the nation. Okay. They have more cows than people there, actually. That's what I heard. But it was a beautiful place. But anyways, you know, these are the kinds of problems you can calculate with the fundamental counting principle. And so what I'm going to do next is ask another question that I think is kind of interesting because, well, it's spring and I guess you're learning a little more about me as we work together. So I'm a huge, huge baseball fan, okay? Actually still play. I've played since I was a little kid, you know, and I love it. And in baseball, so how many players are there on the field at once? Okay, so some of you know the rules. You're going to have 9 players out there. And the question I'm going to ask, which I think is an interesting question to ask, is how many different lineups are possible? You know, with all the success the Indians had last year, Terry Francona, I mean, people love him here in Cleveland, right? And what's he do? I mean, he sits there and he makes up the lineup, right? Suppose you only had 9 players, right? Let's say with 9 players. So all you have to do is decide who bats first, who bats second, who bats third, right? How many different lineups are possible? That's the question I want to answer. I want you to understand this is not a simple question to answer because there's a lot of possible lineups. And that's why I want to thank Jared, Sierra, and Amy for volunteering. That was really kind of them. So thanks. They're going to stand up for us. They had their hands up. They're in the back. You couldn't see them. So one of the things that we do when we want to solve a difficult problem in mathematics is we say, wait a minute, let's solve an easier version of the problem. Suppose there's only 3 people on the team, and we're going to make a lineup. And so you'll notice that the way that they arrange themselves right now, I see Jarrett is leading off, okay? And batting second is Sierra, because she can go both bunt and hit for power. And then Amy's going to knock them all in because she has that great batting average, right? So that's their batting average. But we don't have to do it that way, right? So could you guys rearrange for us and show us what else is possible? We want to count all the possible ways. So there's another one, right? We have J, A, C. Okay. Are there any others, possible ways? Tell me what we have, guys. Wait, you got to pick. All right, what are we doing?
Okay.
What's this one? Help me out, guys. AJC, I agree. Okay. And then, are there any other possibilities? Okay. What is this? CAJ. Are there any other possibilities? How do you know?
CJA.
Oh, yeah, right? We have to be careful here, right? CJA is another possibility. You have another one? You guys, let's see it. I want to see it. Jerry's not used to batting third. You got promoted, kid. All right, so A, C, J. Are there any other possibilities? How do we know? Like you guys thought we were done with 4 at one point, right? You think we're done? I mean, I'm counting. There are 2 when Jared bats first, because you could swap either of those. There are 2 when Jared bats second, and there are 2 when Jared bats third. Like if you just kind of look at one. So what's the answer? The answer, if there's 3 lineups, would be 6. You with me? All right. Now, we're going to add Sarah to the mix. Thanks, Sarah. That was nice of you to volunteer. So Sarah's going to stand up, and she's going to show you. By the way, please understand, we have a lot more possible lineups now, right? Why? Because Sarah, where she's standing right now, is batting leadoff, right? If Sarah bats leadoff, I claim there are already 6 lineups we could have. Are you with me on that? Or if you respect Sarah's power. Sarah, could you just go stand in cleanup position, please? Right? Yeah, try not to kill yourselves back there. If Sarah is over here, I claim there are 6 more orders we could have where Sarah bats. Have you guys followed this? Is there anywhere else Sarah could go? Yeah, second or third, right? So how many possibilities are there altogether when we have 4 people involved? Well, 6 from leadoff, 6 from batting fourth. Now we've got her at third. That's another 6. And she could also bat second. That's another 6. I'm counting 24. Are you guys with me here? So there are 6 times 4, 24 possibilities when you bat 4 people. Now, Brandy told me before class, Paul, don't embarrass me. I don't want to stand up. So I won't embarrass her at all. Okay, but what I am going to do is, if we were to add Brandy to the mix, can you tell me what I would have to do to get the number of batting orders correct? It's actually not that hard. We would just have to multiply this answer by, not 6.
4.
This one we multiplied by 4. Why? Because there were 4 places Sarah could go. Once we have Brandy, there are 5 places Brandy could go. So you take this answer and multiply it by what? By 5. And you'll notice, watch. So there's a mathematical symbol for that, right? This 5 times 4 times 3 times 2 times 1, we write it this way. It's called, 5 factorial. Thanks for helping, guys. 5 factorial. It's not 5! Sometimes people think that's what, but it's not. It's 5 factorial. All right? And so on the calculator, we can now compute how many different lineups are possible with 9 players. It would be 9 factorial, whatever that means. It's a large number. How big is 5 factorial? Anyone work it out? 24 times 5? 120? See, on the calculator, you can get that in the following way. You could say 5, and if you want to get the exclamation point, here's what you do. You're going to hit the math button. Where's that? Right here under the, right? And then I'm going to hit the right arrow for a little bit because I want to move over until, do you see that menu that says PROB? Do you know what that stands for? You're probably right. So then we're going to go down to choice 4, right? And that exclamation point will show up, and that's factorial. So 5 factorial is 120 different lineups, but of course what we don't want 5 factorial for Terry Francona, we want what? 9 factorial? And so these lineups, wow, just with 9 players, there are 362,880 possible lineups. Pretty cool. And this is where counting, really comes into play. I mean, here, move the clock. I don't need you timing me. So, this 9 factorial, what did I say? Just lost it. Yep. Okay, there we go. About 36,000.
300.
Thank you. 362,000?
Yep.
880. That's better. So there's a lot. Sometimes people wonder, hey, what about playing cards, And I deal the cards, so I shuffle them. How many different ways could those cards be arranged? Well, now you know. What do you type in? 52 factorial. Here we go. Again, it's math menu, probability, and choice 4. Holy moly! What's that mean? How big? An 8 with how many digits after it? 67 digits after it? They don't have a name for that number. Zillion? No, that's not a real. Yeah, that's a lot of possibilities. And so one of the reasons that when you study probability, you better study counting is because the numbers get really big really quickly, right? And what we're counting here, by the way, okay, when we say how many different lineups, we're really counting, right, number of arrangements, right, or orderings. And these are also called permutations. Permutations. Okay? And that's an important idea. Whereas there's another word that we talk about when we talk about groups. And the number of groups where we don't care about the order, that's combinations. Combinations. Someone used the word combination the other day, and I wanted to make sure, was it you? I wanted to make sure I drew the distinction. There's orderings where you care about the order, but then there's also combinations. And I thought to demonstrate combinations, I'd go right to the book and get a problem that kind of demonstrates that. Suppose I decide to exempt 3 students from Friday's quiz. Yeah, I'll just give them an A automatically, right? Well, suppose I say that's the deal. Here's the question. In how many ways can I do this? Well, what's the information we need? How many students? All right, well, let's count. I see 3, 5, 7, 12 are here. I mean, you have to be here, right, when the announcement happens. That's fair, right? Or should I just exempt the 3 that didn't show today? No. You got to be here, right? So we have 12 students here. So one way I could do it is I could just say, okay, line up, right? Then I'll just take the first three. I'll take the last three. They were my volunteers, right? How many different ways could we choose 3 students that way? Well, how many different ways could I have the 12 of you line up? That'd be what? How big? We actually should know this. How many different ways can we line up? Not that you're going to compute it. Well, you might. But the basic formula is 12 factorial, correct? That's the formula. But here's the thing. If we had you all line up, so suppose you do, you all line up, and so who's where? We have, well, at the very last 3, the ones I'm going to choose, suppose that again is Jarrett, Sierra, and Amy, right? And you have all the other ones here. You with me? That'd be one way of doing it. I could mix you all up, and whoever the last 3 are, that's who we get, right? But I claim that this number, 12 factorial, is way too big for this problem. Way too big. There's not that many ways. And the reason is, let's see if this makes sense to you. If I have all these people like this, and suppose at the end the last 3 were these 3, A, C, J. Suppose that were true. I would still pick the same people to be exempt. Does that make sense to you guys? And actually, we already computed. How many different ways could I arrange the last 3? Yeah, because that's 3 factorial. You guys with me on that? So I claim that the answer is not 12 factorial. It's 12 factorial. We need to divide by that 6, which is 3 factorial. But I claim that answer is still too big. And the reason I claim that answer is still too big is because, you guys, how many people are standing here? 9. Isn't it true that those 9 I could rearrange a lot of different ways and they still wouldn't be exempt? So not only do you have to divide by 3 factorial, you also need to divide by 9 factorial. I claim that that is the answer to this question. 12 factorial divided by 9 factorial and 3 factorial. So, let's do that. We have 12 factorial. So again, that's choice 4 here. 12 factorial divided by, and now what I would do is I'd open a parentheses up and I would write 9 factorial, which I think I already have, right? I could just select. Can you just select things? Oh yeah, this is nice. I could just go right there and click on 9 factorial and then times 3 factorial. Well, I'll just write 3 times 2. Oops. I just don't feel like writing 6. I don't know why. Close parentheses. That's the answer. Does that make sense to you guys? That's the number of ways you can choose. So it turns out there's 220 combinations of students. These are called combinations. By the way, there's a faster way to compute it. So the answer is 220. Again, these are combinations. Combinations are when order doesn't matter. And that's why we had to divide so much. I mean, 12 factorial is a huge number, but we divided by lots of stuff here. 9 factorial and 3 factorial. your book has a symbol for this. They're going to write NCR. The number of combinations of n objects taken r at a time. And they'll say it's n factorial over r factorial times n minus r factorial. Okay? And so this would be 12, choose how many? How many are we choosing? Out of the 12, how many did I choose to be exempt? 3. And so we computed that was 220, right? The fast way to do it, and I'll show you this, and then we're done for the day because we got to go after this. Take that calculator. You want to type 12 in. But this time, when you hit the math button and you go over to probability, we're going to go not to choice 4, but choice 3. See that? NCR. The way I read this is 12, choose 3. So 12 is N, and 3 is R, and that gives me 220. So you do that when the order doesn't really matter. Okay? And I guess we'll see more examples tomorrow when we come back to class. Maybe on the homework tonight, too. Although I didn't see a lot.